Okay, welcome students. So today we will be starting with Unit 2 where we will be discussing about gravity field. So in Unit 1 we have discussed the introduction to geodesy and its development, where we have seen how uh, the ellipsoid, geoid and different the shape of the earths were being considered, right from starting from spheroid and then coming to the ellipsoids. And then we have also seen how the ellipsoids measurement from the ellipsoids are taken, how measurement from geoids are taken. So brief history we have already seen, and we have already covered the superficial concepts of geoid and ellipsoids and its historical development. But the thing is now, like, how this how we actually come to get the geoid, how do we measure the geoid, and how we actually try to fit ellipsoid to the geoid. So basically determination of a geoid is actually done by a gravity. So we have to do some gravity surveying and then we actually arrive at the geoid. So here in this unit we will be going much deeper into gravity field in the field of geodesy rather than in the field of physics, geophysics or geological fields. So here we will be basically we'll be understanding the gravity field in the field of geodesy. So there are the gravity fields are used by different like professionals like geophysicists, geologists, and different astronomers. They use this gravity field in understanding. For example, for geophysicists and geologists, they will understand in understanding the rock densities for mineral explorations, petroleum products beneath the subsurface. And for astronomical calculations, they use to know the distance of stars, the size, the shape of the different planets, and then their planetary motions and their governing forces between the planets. So gravity fields are used in these fields. So here in this case we will basically see how gravity is important in the field of geodesy and how geodesy relies on this gravity field. So let's see how it is significant to geodesy. So first things, the gravity field is actually used to determine the reference system for the measuring the quantities like the coordinates, that means latitude and longitude, and also the heights, that means from the surface of the earth. So what is the height on, like, the elevations on the surface of the earth. So these heights are actually governed with respect to certain reference systems or reference surface. So which in this case might be which we have also already discussed in Unit 1, which is your ellipsoid or geoid. So we actually determine these reference systems, and also it is also used in determination of Earth's shape. So how actually the Earth's shape looks like. So it is neither spheroid, neither it's completely perfect ellipsoid. So it is very irregular. So this irregularities actually the gravity surveying actually highlights this irregular surface of the earth. But when we see from the space, it actually looks like a sphere, but it actually is not so. So gravity surveying actually helps in identifying these irregularities of the earth's surface. And also once we determine this irregular surface, we try, and this irregular surface is actually termed as geoids, and this irregular surface that is just like measuring a contour lines, we measure the equipotential gravity field. So this equipotential gravity field is actually a geoid, which is also known as a level surface, or which is parallel, or which is equal, which is around the mean sea level surface. So we can say around the mean sea level, the geoid forms the proper shape. So that is your geoid. And another one is it's used in, like, for getting the informations about the interior characteristics of the earth, like densities. You try to see the rock densities and all. So this gravity is used in this one. So this is geophysicists use this information of the gravity. So geodesy also becomes a part of geophysics. So this is the importance of gravity in geodesy. So they completely rely on geodesies for proper and accurate measurements like latitude and longitude. And this latitude and longitude are basically we determine from a reference system, which in this case would be like ellipsoid. And I have already discussed in Unit 1 that this reference system, one of the reference system is like WGS 1984, which is an ellipsoid to measure the coordinates as well as the height of the object from the on the surface of the earth. And also GPS also makes use of this ellipsoid as a reference system for measuring the elevation on the surface of the earth. So this reference, the ellipsoid becomes the reference of the earth, and this ellipsoid is actually approximated from the geoid, and this geoid is actually nothing but the gravity measurements. So we get it by measuring the gravity on the different places of the earth. So this is how we use gravity and how geodesists use gravity, and how they determine how it actually used in the measurements of quantities like the coordinate systems and its height. So this is the brief thing. So let's see how do we actually measure gravity. So there are certain devices that uses the functions of the springs to actually measure the gravity. So here the instrument that or device that measures the gravity is actually known as gravimeter, wherein the instrument is fitted with some kind of spring inside the gravimeter, and the deformation in the spring is which actually highlights the gravitational pull of the earth, and that deformation is actually very it is very sensitive, and then we cannot actually see the deformations particularly. So some kind of laser light is used to actually determine the how much the deformation is taking place in a spring. So with help of these deformations, we actually make use of the calculations of gravity. Some of the instruments are devised in such a way that they are directly hanging in a vertical way. So this is how it looks like if it is vertical. So once the deformation is taking place, so we can actually measure the gravity. So we'll see in the subsequent slides how do we actually take into consideration the other deformations. And another type, there are some other instruments in order to increase its sensitivity. So the springs are at a certain angle. So and then the weights are placed on the. You see here the weights which are placed on the springs, and this at an angle. So in order to increase its sensitivity, so different measurements are taken from this which is hung at a certain angle. So both kind of arrangements can be seen depending upon the type of instrument. Okay, let's see. So how do we actually measure the gravity? Okay, before we try to understand how do we actually measure the gravity with the help of the gravimeter, let's try to understand the types of gravimeter. So there are basically two types of gravimeter. One is absolute gravimeter, which is in this case I have shown you in the earlier slide, it's a basic gravimeter, and there is another gravimeter known as a relative gravimeter. So in absolute gravimeter, what it does is like it does consider the force of gravity due to moon, the acceleration, centrifugal acceleration due to the Earth's rotation. So absolute gravimeter actually takes into consideration all this, and then because of these considerations, the gravity values tend to differ. While there is another relative gravimeters where we try to take away this effect. So we neglect this effect of the moon's gravity field and the centrifugal acceleration due to rotation of the earth. So here in relative gravimeter we try to let's say in this case we try to subtract these two, and then we actually try to only define the earth's gravity field, neglecting the other celestial gravitational forces. So field or spring gravimeters are not absolute. So this is one of the kinds of relative gravimeters, and then they have a drift. So drift here basically means like this is some kind of techniques to actually to deduce to get the actual gravity field of Earth, where we try to subtract the drift. That means drift basically means like at certain point. Let's say if we measure the gravity at certain point at a certain place. So let's say at a place like Genek in our college. So if we measure at time t equal to 1 hour, so gravity field will be different. At time t equal to 2 hour, now by the time t equal to 2 hour, the Earth would be rotating. So at time t equal to 2 hour, the gravitational pull will be different. Let's say at time t equal to 3 hours, we might reach, and the moon might have some effect at this point of time. So again, there will be a variation in the gravity. So they will have a drift. So and that means acceleration gravity will slowly change over time. So this drift we are actually trying to neglect, or we will try to actually subtract from the whatever measurement that we get. So that is known as a relative gravimeter. It's a relative. So these are the types of the gravimeter here. So like let's see now, how do we actually measure the gravity with the help of the instruments? So the instruments basically relies on the Hooke's law. So Hooke's law is basically it is centered around the deformations of the spring. So as I told you earlier, the gravimeter is actually fitted with either horizontal or a diagonal spring. So if there is a diagonal, it is just meant to increase the sensitivity of the instrument. While but most of this we see device, we also see the vertical cases. So here this is a particular setup where we have a gravimeter fitted with a vertical spring, and then the spring has some mass, and then the deformation or the extension in the spring actually highlights the gravitational force. So how the extension is actually related to gravity. So let's see here. So this is force into mass into acceleration is a general force that the Newtons give. So the force here in this, for this particular setup, force is mass of the spring. So here this is the mass of the spring times the acceleration due to gravity. So this actually we are trying to find out. This is what we aim to. This is our aim, and what we want to intend to get it. So mass times acceleration due to gravity, and this, as per the Hooke's law, is actually the Young's modulus of the spring times the deformation. That means how much the spring has extended or contracted. So that is the value of x. The negative sign simply means that the force is acting downward. So no need to confuse about the negative sign here. So this deformation x, so how much it has deformed or how much it has extended, so x is given by, so just use this simple equation to get the value of x. So we just simplify this equation where we get where the deformation or the extension, spring extension, is actually equal to mass of the spring times acceleration due to gravity divided by the Young's modulus. But our aim is actually to get the g. So g is actually k is Young's modulus. So Young's modulus for a spring, there will be certain value, some specific value, times x. So x is actually the distance or the deformation or the extension of springs, which is actually measured by the laser light. So how much it is extending, so that is measured. So k is known, x is known, and mass of the spring is known. So this mass of the spring comes with the instrument specification. So relying on these three terms, we actually try to get the acceleration due to gravity. So this is how we actually measure with the help of the instrument. So now let's see the governing forces of the gravity. So when we talk about gravity, it is unavoidable to talk about Newton. So Newton's law, he is the one who actually came up with this idea, the force of gravitation. So this force of gravitation, so the Newton states that the force of attraction between two masses, so m1 and m2. So m1 and m2 can be any masses. It could be on the surface of the Earth, it could be beyond our the celestial bodies or beyond the solar system or within the solar system. So separated, which is separated by a distance r, is given by force is equal to g, which is the acceleration, not acceleration, it is a gravitational constant. So it is it remains constant, and then the m1 and m2 are the subsequent masses. So if it is on the surface of the earth, so one m becomes the mass of the earth, another m becomes the mass of the object on the surface of the earth. So and r here, it's the radius of the earth, radius of the earth if the object is on the surface of the earth. But if this object is like between moon and the earth, that means what is the center to center distance between the earth and the moon, so that becomes the radius. So if you want to find the force, so what is the force of gravity, the force here between the two objects, so that force is actually, we try to govern by this formula. This is the same one here, g into m. M is the mass of the earth, small m is the mass of the object on the surface of the earth. If you are trying to find out the acceleration due to gravity, and the force, not acceleration due to gravity, but force due to gravity on the surface of the earth divided by the radius. So if it is on the surface of the earth, if the mass is surface of the earth, so r is actually the radius of the earth. So this is how we get the values of force. But since we already know force is also mass times the acceleration due to gravity, so we can actually get the acceleration due to gravity. Just simplify these two equations here, this equation here, and then we simplify, and then we get that g is nothing but it is gravitational constant times mass of the earth and then the radius of the earth square. So, but looking at this one, you see this g is also constant. Okay, so g is constant as it is this value here. M, the mass of earth doesn't, this is also doesn't change, mass of the earth doesn't change, and r is the radius of the earth, and radius of the earth also doesn't change. So looking at this mathematical representation, it seems obvious to us that the acceleration due to gravity remains constant. But this is not the case, because as I have told you while explaining geoid in the earlier classes, that the acceleration due to gravity differs from place to place depending upon its the irregular shape, rotation, internal mass distributions, and because of all these effect, there is a changes in the gravity. And then although the mathematical representations tends to give a constant value of g equal to 9.8 meter per second square, but this is not the case. So it will vary up and down. For example, in case of in and around the equator, since the equator is having a bulge, so it is further away from the center of the earth, so it will have a lesser gravity field, while around the poles we have a like flattened poles, so it is nearer to the center of the earth, where we will experience a higher gravitational force. So it will be constantly changing, and also due to the internal mass distribution, some of the rocks, they will have higher density. So around those higher densities, like example where there are mountains and also, they will slightly experience higher gravitational pull, while around the plain areas it will be slightly lesser. So there are some relative variation between the gravity, so it is not constant throughout the earth. So this is what the Newtons gave the idea of the force of gravity. So after Newton's, there was one revolutionary idea proposed by the Einstein, so who also augmented on the Newton's law, while not defying his idea of gravity. But the Einstein proposed that gravity is like a wave, and then like in the space-time, and then it can be, the gravity can be bent. I mean, like it has some wave, and then it can actually bend the light. So till now, around 1600, it was assumed that light was traveling in light cannot bend and light travels in a straight line. But after the Einstein's theories and Einstein's proposed his ideas, so they found out that light also bends. So this bending of the light is basically due to gravity. So if you have a higher gravity or higher mass, so higher the mass, so we will experience higher gravitational force. Like example, like sun. So light can bend around the sun, and if there are any objects behind the sun, that can be seen by on the surface of the earth. So even if the black holes will also have a higher mass, that means it has got higher gravitational pull, so light cannot escape the gravitational field of the black holes. So light will also try to bend, and so whatever objects that are beyond the black holes can also be actually seen. So that is the concept that the Einstein actually highlighted. So so let's understand now how what are the units of gravity, and how do we give, because gravity, since it is very sensitive as I told you, and it varies by on the surface of the earth, we need to understand the its unit. So usually the unit of gravity is given in milligauss, and this 1 milligal is actually 10⁵ meter per second square. So it has got 10⁻⁵, so it's very highly sensitive. So these are because of, since it has got a higher sensitivity, so that's why the whatever the instrument measures, so it is measured in milligauss. So sometimes we can also measure it in gauss. So gauss is actually named after the Galileo. So this is the unit that we actually used for measuring the gravity. Okay, and then since we before understanding the gravity potential or gravity potential lines, we need to understand the contours or the height gradients. So how does this behave, and then we try to understand how the gravity actually vectors behave, what are the different types of gravity vectors. So first let's understand what is the height gradient or height contours.